Hello, everyone. Welcome to another episode of our Summer Kids Club with the Aquarium Online Academy. My name is James. I work in education here at the Aquarium of the Pacific. First off, let's apologize for our 11 o'clock class getting abruptly ended while we were just getting into some of the fun. We had some technical difficulties that cut the stream, and we can't restart it once that happens. So, let's have some fun for this class. Youth scientists, are you ready to have some science fun with me? I love science. You love science. Let's do it. So, I got Jen on question control. She's a great scientist, too. Ask her really tough questions. She usually writes down the hard answers for me, too, so that way I don't have to answer all the hard questions. Carrie's on the control for the stuff behind me here, but we're not just going to look at stuff in the ocean today. We're going to do some exploration to discover Earth. Found it. All right, next step. I'm just kidding. Well, you get to participate, and there's actually a couple ways you can participate today. The easy one is to text us questions here at 562-286-1838. Now, the other fun way that you can participate is we're going to be using a special mobile device app called SOS Explorer. This is a free app, so if you have permission to download things on the device you're on, you can download the SOS Explorer app on your device and follow along with us. I actually have it on my phone. Sometimes I play with it. And it's kind of fun to get to explore all the really interesting ways we can represent data, numbers, fun things. If you just look at a chart of numbers, some of you will enjoy that, but a lot of us need something else to envision what that means. What's the context of that? Well, the SOS Explorer really helps because we can take all this number material that scientists have collected and put it into a more meaningful format that allows us to understand what's going on. Just like if I only gave you number data about kelp, you might mean something, but it doesn't give you the same context. So let's start exploring with our SOS Explorer. Now, I have a special iPad. It's actually on my extension cord for my iPad needs an extension cord. So I have to sometimes stand off screen to help explore our Earth with you today. All right, here's the cool thing. This app can also show some videos. So we're just going to look at the data sets, not simply the videos. Now, what that means is some of those videos are going to have sound to them. So if you start exploring around not where we're at, it might play something new for you. But this is what I'm looking at currently. This is the kind of standard picture. Now, I can spin this around. Whoa, did you feel it? Yeah. Just kidding. I don't have that much power. But this is one of our really amazing educational tools. So scientists make observations, and we ask questions, and we learn from those questions and those observations, and we ask more questions. So let's make some observations and see what we can find out about the Earth. It's round. Good start. We already had some information coming in. Oh, Jen said she could feel the Earth move. She loves the Earth, and it's okay if it moves a little bit. We're actually going to talk about the Earth moving that you can feel today. We live here in California. This happens every once in a while. So it's kind of fun for us to talk about. Let's talk about this part first. We have this very beautiful 3D image of the Earth. The cool thing that we can see here is our DayNight Terminator. Not like a robot from the future, but a line that allows you to see the nighttime half and the daytime half. So if you had to guess, what side would the sun be on? Is it on that side or is it on that side? The sunlight would be coming from there to here, so it's displaying on our Earth. Now over here is the nighttime side. We can even see some nighttime city lights. Now I keep checking the screen below me to make sure I'm pointing at the right thing, because if I'm pointing here talking about city lights, that's the middle of the Atlantic. There's nothing there. There's some cities. Oh, somebody texted in observations that they can see the clouds. Good job. If I spin this around to just the daylight side, there's a lot of clouds that can be found. There's actually a special group of clouds right there. What is that? Did you find it if you're following along at home? If you were playing on the SOS Explorer, did you see what this was? How do you recognize what this is? What observation did you make so you understood what this is? The swirling is often a common thing that people tell us about. They see the big swirlies. This is a very special swirly. It's called a hurricane. Were you thinking that too? Yeah, sometimes we get people asking us about tornadoes. Can we see tornadoes on this? This scale would be way too big to see a tornado. A tornado would be a very tiny little dot, if we could even see it at all, because a hurricane can be hundreds of miles wide, whereas some of the tornadoes might only be 1 to 2 miles wide. And 1 or 2 miles on this scale is extremely tiny, very tiny. So, well, we want to look at the big stuff, like the hurricanes. Now, what else besides this swirl told you this was a hurricane? How about this little part right here? The eye of the hurricane. Now, a good question came in is, do these satellite images ever do this in real time? Now, I'm guessing this one, I'm going to zoom back out, is actually pretty close to real time. Because if I spin this back to Europe, that's too far. That's past Europe. Let's go back. Doop, 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 doop. There's part of Europe. Right here. Now, they are in the nighttime part of the day, because I think England is 8 hours ahead of us right now, and they're right about there. So that puts them from Pacific time, 9 o'clock. 9 o'clock should be pretty dark. So this is probably pretty close to real time. Now, this is not a real image. This is a computer-generated image of the real things that they are measuring and that they can see, and other pictures that they can take. So a lot of you texted in that you can recognize the hurricane. I'm spinning the earth off camera, sorry. All right, so here's our hurricane. Now, if you live in Southern California, like we are here in Long Beach, you might be feeling the excessive heat that's outside right now. Woo, is it warm. This hurricane and the effect it's having on the atmosphere right here is creating a lot of moisture-laden hot air. So we get these effects where there's warm and cold and wet and dry air mixing together, creating a very unique effect where we're at. And it's basically what we call a ridge, which is a very high pressure or warm center of air. And this hurricane, because the hurricanes are spinning this way, is causing some of that air to get pushed and stayed on top of Southern California. So, if you really like meteorology, tools like this are great to study meteorology, how you would study weather. Now, weather and climate are very different. Climate is long-term, all the possible effects of weather. Weather's like today. Like I wore this outfit today. Climate is my whole wardrobe. Any possible combination I could ever wear on August 19th on any given year. So somebody's asking, where's the hurricane now? I think it's actually pretty close to still being off of the west coast of Mexico. So here's one of the fun things. On the National Weather Service, or even with NOAA, National Oceanographic and Atmospheric Administration, they're the ones that actually created this stuff. You can check out their hurricane tracker and watch where the hurricanes are going. Do you want to learn more about some hurricanes? I think we have a decent hurricane video or a map set that we can show you of Hurricane Sandy. So this has been a few years now since Hurricane Sandy, but we're going to get to check out what it did over here on the East Coast. Now, the unfortunate part is because this device is not the same setup that we have. Like we have a whole room with a giant globe in the middle of it that we can show this information on. When they try to condense it to our mobile devices, it doesn't always look the best. So we'll try to get you a really clear picture of it. Okay, if you're going to follow along with us at home, there's this green set of arrows right here. I tried pointing it on my iPad. You can't see my iPad. Right there, you push that little button, you get to see our all possible different maps that we're going to show off. Now, I'm going to scroll down and look for some different maps. Do I have a favorite type of weather? Not hot, that's for sure. Let me tell you that. That's not my favorite weather. I don't like humidity that much. I grew up in a semi-arid, almost arid area, which is like almost desert. Humidity is not my favorite. We need it. We need moisture in the air, but this just doesn't feel nice. All right, so I'm going to click on the air icon, and this gives us only maps that concern about air, okay? Well, let's look for something with a hurricane. Ooh, Hurricane Sandy, 2012. I'm going to click that one. Let's click Hurricane Sandy. Give it a second to load. Loading. Okay. Now, the cool thing is we have this play bar right here. So if you're following along at home, you can slide the play bar along to look at different things. Now this feels a little bit more Weather Channel style, right? Here's our air mass. We can see it starting to build a lot of volume and spinning around. There's a different air mass right here spinning, but that's not a hurricane. Remember, we want to look for the eye of the hurricane. Follow it along. Oh, Sandy got pushed back into the United States. So that was kind of the interesting thing about this storm. I'm going to let it keep playing so we can just watch where everything is going. The cool thing about hurricanes is, I mean, they are very dangerous weather patterns, but the cool thing is they get so massive. The reason they start spinning is because the Earth is spinning. If the Earth didn't spin around, these storms wouldn't do this. So we have to be spinning around on our axis. There's so much mass from the clouds, so much weight, that they start spinning around in what we call the Coriolis effect. So there we go. We get to watch it. Good question came in is, if Mexico gets hurricanes, can California get them? Well, while Hurricane Sandy's going, let's actually take a look at the other part of the United States. And let's see if we can figure out the direction the winds are moving. So down here, where Mexico is at, I'm going to zoom out, actually. Let's do one of these. Let's take a look at some of the wind patterns versus latitude, so how north or south you are, okay? This is the equator, like the Earth's belt, a belt of clouds right there. What direction can you tell the air's moving around the equator? So we have this empty spot of clouds right here. So these clouds look like they're going very slowly this way. Let me hit play again. Boop. It's thinking about it. Okay, well, right here, the clouds are very gradually going this way. And then above the equator, they are very gradually going this way. Let's see if we can restart it. Sometimes the internet in this room doesn't work well because we're under many feet of concrete. All right, here we go. See if we can get it to go. It's thinking about it. It's trying. Well, okay. So what we're trying to show you, but is not working, is the trade winds. So right here, across the equator, the winds go one direction. In the trade winds right here, they go another direction. Same thing on the bottom here. They move this way. This is also because the Earth is spinning. But before we talk about the spin, we have to talk about the sunlight. So the sun blares at the Earth, right? Lots of heat is coming to us. But does everywhere get the same amount of heat? Maybe, maybe not. Does it look like there's just as much heat up here as there was down by the equator? No, we actually get uneven heating. And some of it is because of the curvature of the Earth, but some of it is also because of the tilt of the Earth. The tilt of the Earth is the reason for the season. Have I ever underestimated the impact of a hurricane? I've never experienced one, so no? I don't know. You actually can underestimate it because some things are going to happen in the pattern that we'll try and rewind and show you again. I might have to mess with the iPad, and we'll switch to one of our webcams while I mess with it, try and get it to start back up. But we get uneven heating of the Earth's surface, and that causes wind. And the wind would normally just flow from the top to the middle, and then back again, or from the bottom to the middle, our equator to poles. But because the Earth starts doing this and spinning around, we get all these other weather effects. All right, let's try reloading our Hurricane Sandy and see what happens. All right, now it should be doing what we need it to. Let's spin the Earth about right here. Take a look at the cloud movement. So right here across California, we're getting these clouds pushing against us. Now, the other thing that will not easily create hurricanes for us is that this is cold water compared to what they get in the East Coast. So they have a warm water current pushing up towards Europe. We have a cold water current that pushes down from Alaska. So the water is almost too cold here to create a hurricane. Hurricanes have to start in about 80 degrees of temperature in the water for about 50 to 80 feet of the water. It takes warm water to start this up. Now, when you underestimate a hurricane, it could be because it moved over land. But then it goes back to water. And then it gets pushed along the coastline here. And then they're like, oh, Hurricane Sandy's done. You know, the Carolinas, they dealt with it. It's just going to be a big storm now. But then the winds changed and it pushed back into the United States. So it caused some double effect of weather patterns on a lot of areas, causing a lot of flooding. And that's how we might sometimes underestimate what a hurricane can do, because we don't know exactly where it's going. Meteorologists are not fortune tellers. They can guess based off the data at hand. Well, sometimes the Earth's like, nah, watch this, and it changes the effect very suddenly. When you watch those hurricane maps of where they're guessing it's going to go, that's why it ends up in this big V's, because like, well, we're guessing it's somewhere in this cone of danger, and then it might move left or right inside of there. It might go very straight. We have to wait and find out where it's going to go. With more data, with more that we know about hurricanes and storms, we might get better at guessing where they're at. And we have in the last 50 years because of satellite data, but we still need to learn more. That's the great part about science, is you never stop learning. Okay. Well, now we talked about the air. Let's talk about the land under the water, not just the stuff that we stand on. I want to show you a really fun map. Oh, I got to change back to a different playlist. Actually, let's go with water. And here's our water playlist. There's a lot of information in the water playlist. Since we're the Aquarium of the Pacific, we should know a lot about the water, right? And then suddenly the map I wanted, I can't find. Let me look for it real quick. It's called Ocean Drain. Let's go back to this, and now that we're alphabetical, I'm looking for a specific map that's going to show us what the Earth's surface looks like without water. And here we are. Ocean Drain, or what we would call bathymetry, study of the seafloor. So let's get rid of our little notice. I know the Earth is not flat. Thank you. All right. Let's just pause that and rewind. What happened? Here's the Earth like we would normally think of what's going on with Earth. But now imagine somebody pulled a plug in the bottom of the ocean like a drain and just let all the water drain off Earth. The areas that would be exposed first would be the shallowest. Imagine like a bathtub. You filled your bathtub up with water. You pulled the drain out. What part is the first to get exposed? The top of the bathtub. What part is the last to get exposed? The bottom of the bathtub. So when we play the Ocean Drain video, we're going to watch the water pull away from the coastlines and then gradually move towards the deepest sections. So let's go to, I'm going to skip to the very last image, or try to. There. Well, that's almost the end. So this is what the Earth looks like without water on it. This is really, really different than we might expect. When we look out at the ocean is flat for the most part. We don't really think of everything underneath the ocean as being textured like this. These are mountains and canyons and chains of these large abyssal plains, or this wide open and flat, but it's very deep in the water. And we may not expect to see all of these different features under here. Someone's writing in that the seafloor looks gray. Yeah, this is a false color image. So if we went down there, it wouldn't, well, parts of it would be gray, but it could be other colors too. This is just the colors that they created for this map set and what it would look like without the water on it. Now, the different colors of the seafloor would come from different kinds of rocks and minerals, and potentially things that are living on it or not living on it. Lots of different effects. So when you have a rock that is red, it's because of the iron in it. If it's not very red, it has actually a very little amount of iron in it. So sometimes the colors that you might see in here, like someone said red rocks in Arizona, is because of something called feldspar. I love that, feldspar. It's got lots of iron in it. That's all it is. So it's a special kind of rock that has more iron than others, and that's what causes the redness of certain rocks, like Arizona, parts of Colorado, Utah. It's very red soil because of iron. So let's say this patch right here had a lot of iron in it, it would probably be more red. But since we didn't take a picture of it, we may not know. It's also harder to do that scaling at this level. So the people that created this map just made everything gray. So it's a little bit easier so we don't have to guess what colors there are. Now the cool thing when you look at this is that all this texture is caused by tectonic activity. Have you heard of tectonic plates before? One of the fun things we can do with this setup is I'm going to click the overlays. We can actually look at different things. The different maps have different overlays. This is just another way to start separating the information out. So if I want to look at what countries were where, I could look at the country borders. If I wanted to look at the grid lines of the latitude and longitude, I could add that too. Right there. Now, ooh, good question. Can minerals oxidize in water since water is made up of oxygen? Well, yes and no. So it depends on what you're looking at. So if I put a old truck in the ocean, which, you know, sometimes that happens. Not me personally, I didn't do it. But it gets in there, the metal rusts because it starts reacting to oxygen. So that's the iron atoms and the oxygen atoms fuse together to create iron oxide. So it's a whole new thing. That's what rust is. It's a whole new product. Well, if it already has a certain structure, it has to be able to react with the oxygen. This red rock, feldspar, has already reacted with oxygen, so it's starting red. As far as I know, you can't make it more red by putting more oxygen around it, even if it was part of water or oxygen in the air. But that's why some things rust, is because they actually are reacting with the oxygen around them. Now, there's also oxygen dissolved into the ocean. So it's not that the iron is suddenly breaking apart a water molecule and putting oxygen on itself. There's oxygen in the water that the fish breathe, that's what it's reacting with. So that's why even if it's underwater, it'll still react with oxygen and get rusty. But as far as I know, the rocks aren't spontaneously reacting with the oxygen that way. It's already part of their molecular structure. Cool questions. Well, let's get into the next part, because we only have a limited amount of time to explore all of the Earth. And that took humans hundreds of years, and we got to do it real quick. Okay, the next topic I'm going to go with is something that we experience in California a lot. Earthquakes. Have you ever felt an earthquake before? The first one I ever felt when I moved here scared the bejesus out of me, because I had never felt an earthquake. I grew up where there were no earthquakes. So it was very disconcerting to understand that the Earth actually is moving a lot beneath my feet. Pretty interesting effect, though, and why it does this. So this is going to be a map of all the earthquakes from, I think, 10 years of time. Oh, no, 14 years of time, 2001 to 2015. So if you're following along, you're looking at the earthquake map on a device at home, what you'll notice is, ooh, let's rewind a little bit. The big earthquakes, no, rewind, thank you. The big earthquakes that you might see the size of the bubble go up, they'll shrink back down over time. Those bubbles shrink back down. So that way we still get the dot left over from where the earthquake happened, but if we just left it at the full size, we just cover everything. So there's that really big one that was in, that looks like part of China and Mongolia. Another one in the Middle East. And as you spin this Earth around and start looking for those really big earthquakes, what you might notice is that there's areas that they like to be in. Now, the color of our dots is the depth. How far into the Earth's surface was the epicenter, the very middle part where the whole thing started. How far into the Earth is it? So red is near the surface. Purple is farther in. It says it's the scale of 800 kilometers. That's about half a mile. That's a really big one. Now, you might recognize some of the timelines in some of the earthquakes that have happened. If we spin this around into the middle of the Pacific, we get a scale for the really big ones, 7, 8, and 9. So there's a lot of activity happening in very specific areas of the world. Well, why is it happening so much there? Why are we seeing a line of earthquakes in the middle of the Atlantic, but there's nothing happening in the middle of Africa over here? Maybe a little bit by Lake Victoria, but not much happening up here. What's going on? Why is there a difference in where we see some of these earthquakes? Or even, you just tilt it up a little bit, The Mediterranean has a ton of activity. What is happening? Why is there a difference of where the earthquakes happen? Well, if you click into the overlays, oh, it doesn't have it. I thought it was going to have the tectonic lines. It doesn't, but that's okay. What we're seeing is the physical data of where the edges of the tectonic plates are. So where there's a lot of these earthquakes happening, there tends to be a split between layers of the Earth's surface. So earthquakes either go side to side. There's another big one over there. Earthquakes either smoosh parts together, or from the smooshing together of the Earth's surface, or they pull apart. So in certain parts, like Indonesia, what's happening is the layers are being smushed together. So you get what's called subduction zone. So part of your surface is getting tucked underneath the rest of the part right here, and it causes a lot of earthquakes. In other areas, you're getting volcanic activity, hot spots, like areas that seem to be occurring in the random middle locations of the Earth's surface. And this playlist hasn't started over. This is still all 15 years of this information. And now it started over. Let's go back to the end. And we'll pause. If you noticed some dots right here in the middle of the Pacific, what happened here? This is nowhere near the edge of the Pacific plate. What's going on? What island is this? Or chain of islands? This is actually a very long chain of islands. The 8 main islands are Hawaii. Now, what's happening is that this is what's called a hotspot. So there's magma bubbling up underneath the Earth's surface, hitting the surface of the Earth, creating these volcanoes on the Hawaiian Islands. The cool thing is you can actually track the Hawaiian Island age by going through this line. These are the result of those hotspots where they would create islands over millennia, and it suddenly took a dog leg from one direction this way. Well, that's because the Pacific plate changed direction. So right now the Pacific plate is going this way. So it's just gradually going that way. And you get new islands. There's actually a new island that'll form over here. I think it's supposed to hit the ocean surface in about 10,000 years. Get your oceanfront property now, because otherwise it's going to be all busy later. So you can actually see that there's the ancient Hawaiian archipelago, or chain of islands, that are no longer above the Earth's or the water surface, but they're still above the Earth's surface. Otherwise, it's not really a mountain. They're still above the Earth's surface, but they're underwater. They've eroded down. Someone texted in that they felt an earthquake in Augusta a few years ago, and it scared them half to death. It's pretty frightening because it happens real suddenly. It's not like the forecaster's like, well, tomorrow we're expecting a 4.5. They don't know. We can guess it might happen in the next 100 years somewhere. But it's kind of hard to nail it down to like August 20th. That's it. That's the day. It's too tough because there are so many unknown variables to estimate that. I was scared too when it happened to me. And, you know, there's a lot that we need to know what to do during an earthquake. But that's the different class. Okay. Next question is it correct to assume the earthquakes come from the same spots in the world? Kind of. So the earthquakes are happening in a very specific region. These are the barriers around the tectonic plates. Sometimes earthquakes happen in areas where there's no tectonic plate barriers, but there's old fault lines. So these are still cracks in the Earth's surface where you could experience some movement. Actually, where I grew up, over here in the middle of the United States, I grew up about there. There have been some earthquakes, but they're the result of other things. These are old fault lines that used to be fused, but because of some of the activity that we've been doing as humans has caused them to open up. That's called fracking. So they're introducing fluid back into the Earth's surface after taking out natural resources, the fossil fuels. And what happens is they got to pump something else back in there, and it starts to lubricate or loosen up those fault lines. So this has been happening in Oklahoma quite a bit too. Really interesting question is, can you fall into the crack between the tectonic plates? Kind of, yeah. It's not like a little tiny, okay. It's not like there's somebody just drew a line, like that's where it would be if it was there. You can actually see the San Andreas Fault from the top of a mountain. You could actually crawl into part of that fault line if you wanted to. I wouldn't, because that's where the earthquakes happen, so I wouldn't do that. But you can see and actually get into these spaces. Sometimes you can actually look at images of where parts of the San Andreas fault system, because they are sliding past each other, have split, and an entire street just suddenly is 10 feet from the other side of the street. So you can see the effect of fault lines and these barriers of the tectonic plates. You could go explore that. So if you were a person that studies earthquakes, if you were a volcanologist, a person that studies volcanoes, you could see these cracks in the Earth's surface and actually get to explore and learn more about them. Good questions from people. We have run out of time talking about Earth. Man, I'm glad we got the entire Earth history in 30 minutes. We have so much more to learn here. Now, tomorrow, youth scientists, you're going to be doing some more fun things, but your activity that we had listed for today is another observation activity. So we practiced using some observation skills today. The next one you have on for the activity today is a bingo sheet. So maybe you or your friends can connect virtually, play bingo with your nature observation bingo, and try to find all the different things in the bingo sheet if you can. And one way you can practice, practicing with our webcams. These are one of our live webcams that you can check out any time of the day. Now, tomorrow, you scientists, you're going to be doing the science of scuba diving. That's a really cool topic, because if you wanted to go explore in the ocean, unless you're in a submarine, you might be only diving at the surface of the water. So we'll learn more about the science of scuba diving tomorrow in our next Summer Kids Club activity. Thanks to everyone for joining us and learning about tectonic activity, hurricanes, all that fun stuff, and we'll see you again tomorrow.